So let's do another example problem here. So let's do an example problem in which we are looking at a rocket deploying a satellite. So what happens is your rocket launches, drops off the first stage, second stage is still attached to the satellite. And so let's say that the second stage is attached to the satellite, and together they're moving at 7,600 meters per second. Okay, and the second stage, we'll call this mass 1 and the satellite mass 2. So let's say that mass 1 is 200, and let's say the upper stage when it's empty is 290 kilograms, and mass 2 is 150 kilograms, so it's a little small satellite. And then what happens is that they separate, and so now the satellite is moving over here with some velocity vs, and the second, well, I guess we can call that v2, and the upper stage is v1, and now there is, we're going to call it vs, a separation velocity. So let's say they're separating at a velocity of 910 meters per second. So what I want to know is what's v1 and what's v2. Okay. All right. So we want to solve this problem. So conservation of momentum, P1 equals, or the P initial equals P final. So P initial would be when the two of them are stuck together. So they're stuck together, object 1, object 2 right here. Okay. And they're moving together with velocity is 7,600 meters per second. Okay, so in this case, P1 is going to be M1 plus M2 times the 7,600 meters per second. And so that's going to be equal to the total right here. Okay. And so afterwards, P final, we have object 1, we have object 2, okay, and so now we know that, and what I'll do is, to make the math easier, I'll just call this V naught for right now, okay, so M1, M2, V naught, okay, and so we have the afterwards P1 and P2. So the P final is going to be P1 plus P2. So that would be, so this is P initial over here. P final is going to be P1 plus P2. So this will be M1 V1. That'll be M2 V2. So P final equals M1 V1 plus M2 V2. Okay. And so, so now we have that M1 plus M2 V naught equals M1 V1 plus M2 V2. Now the problem, we don't know either V1 or V2, but we do know that V2 is we do know that as this thing separates, that V2 is separating from V1, and so that means that V2 has to be bigger than V1. We know the separation velocity is Vs, and so that means that we can then say that V2 equals V1 plus Vs. So if I take that and plug it in right up there, M1 plus M2 V naught equals M1 V1 plus M2 V1 plus Vs. Okay, and so M1 plus M2 V naught equals M1 plus M2 V1 minus M2 times Vs. Okay, so, plus M2 Vs. So that means that M1 plus M2 V naught minus M2 Vs, divided by m1 plus m2 equals v1. So v1 is, after you plug in all the numbers here, 290 kilograms plus 150 kilograms times the 7,600 meters per second minus the 150 kilograms times 910 meters per second divided by 290 kilograms plus 150 kilograms. V1 is 7290 meters per second. What about V2? Well, V2 is V1 plus Vs, so that's going to be 7290 meters per second plus 910 meters per second. So V2 is going to be 8,200 meters per second. Okay. Consider energy. What was the initial kinetic energy? So they're all stuck together, so it's m1 plus m2 times v naught squared. If you plug in the numbers, then that initial kinetic energy is going to be 1.27 times 10 to the 10th joules. The final kinetic energy is 1/2 m1 v1 squared plus 1/2 m2 v2 squared. And so if you do that, the final kinetic energy is, well, actually, we can go one step further. So 1.271 times 10 to the 10 joules. The final is going to be 1.275 times 10 to the 10 joules. So why is the final kinetic energy more than the initial kinetic energy? That doesn't make sense. Up to now, we've always had this thing as less. So what's going on? Why do we have more kinetic energy at the end? Well, think about what happened. We had these two things here stuck together, and now they're separating from one another. That means there had to be some kind of force that pushed them apart. Force times distance is work. Work is change in energy. So we did work on it. Where did work come from? Well, there was like some kind of spring loaded in here, or some kind of reaction jet, or something that pushed the satellite off of the rocket body. And so in this case, the final kinetic energy was more than the initial kinetic energy because there was some potential energy that was stored in the system right here, which then came out. Now, we did not measure that ahead of time, therefore we didn't know about it, therefore we could not have used conservation of energy to solve the problem because we did not know where all the energy was coming from. So this is another example of why conservation momentum is sometimes a more powerful tool than conservation of energy. Energy can sometimes hide in places you're not looking. You cannot hide momentum. Momentum is mass and velocity. You're always going to be able to see the velocity and see the mass in a mechanical system, or you should be able to. So unless you're just not looking at part of the system.